Hi, I'm Ricard Vilalta, Senior Researcher at CTTC and Chair of TeraFlow SDN Working Group at ETSI. So we had a very interesting panel at IEEE NFV-SDN. It was an hybrid panel, so we had some of the presentations recorded, and thus you can see them here in this video. Of course, we had also very interesting presentations live from some of the panelists, which were not recorded, and thus you will not be able to see it. But we think that it's important that you have access to the different videos that were recorded for the panel, so that you can have at least some glimpse of what were the discussions about. And I think that we provided interesting overview of the network automation currently in carrier networks. So I hope that you enjoy the video.
Hello, my name is Daniel King. I'm a consultant at Old Dog Consulting, which is a member of the TeraFlow project. And I'm talking about network automation for carrier networks, the good and the bad, the reality and the myths. So where do we apply automation within the TeraFlow project? Well, actually the applicability is quite wide and varied. So we have at the high level, service automation, application automation, potentially. We've got the overall framework of TeraFlow, which includes several key functional components like the distributed ledger, the slice manager, the lower layer network manager, the context management, device management, automation and policy, and overall monitoring. And then beneath the framework with the individual functional components that are required to deliver the TeraFlow applications and services, we've got the individual devices and interfaces themselves. Before we decide how or why, we really need to consider what to automate. And it has to be underpinned with some kind of business motivation if I'm looking at this challenge from an operator or a service provider perspective. So we have to identify pain points and end goals. So do we want automation to solve existing problems that require significant manual intervention and sending engineers out on site? Is there a requirement from customers to deploy services faster for specific reasons? Does the operator need to increase revenue and at the same time reduce cost? Is the overall systems required to operate the network so complex that if we continue to deploy new technology, potentially we increase complexity of network operation until a point where it could collapse? Once we've decided on what the overall objectives are, we can start to consider which part of the network and at which layer to identify automation and deploy tools to facilitate automation. So it's really important to consider a particular functional component, a technology layer, maybe a vendor, or maybe a combination of interoperability and connectivity between vendors. And then we need to consider how do we negate or mitigate risk for using automation tools in the network to achieve the objectives that we set out. So let's assume that we want to introduce automation and programmability to manage packet over optical networks. So essentially with a focus on our optical underlay. Well, first of all, we need to define the management components, and we can call these functional components, that will be used to design, deploy, and operate these underlay services. So in this example, and a key technology that TeraFlow is using, we use the ACTN framework, the abstraction and control of transport or TE networks. So essentially there are three main components: the customer network controller, the multi-domain service coordinator, and then the ACTN sort of provisioning manager or physical network controller. And these are wrapped up and defined in a document that's published by the IETF, which is RFC 8453. Now, you might use the ACTN framework to manage domains of technology. They could be hierarchical or vertical domains. But you may also want to deploy network slicing, and in TeraFlow, network slicing is a key requirement for how we deploy and manage services. So this framework essentially can be mapped to something called network slicing, specifically IETF network slicing. And there's a second document that's being developed by the IETF called the T's applicability of ACTN to slicing. So we have our problem space, we have the functional components that will define how we introduce automation into the network and what are the functional components and the responsibilities for assisting or facilitating that network automation. Now we need to think about the interfaces themselves and what sort of information we're going to be signaling and requesting and configuring over those specific interfaces. So we have maybe an example of OTN slicing, or maybe we want packet over optical services. So these will be an additional 2 documents that really set out the requirements for managing multi-layer services over complex environments, potentially using multiple vendors and devices. And then a key building block for facilitating automation, certainly in the optical underlay or sort of packet over optical networks, will be how to model the technology and the configuration parameters themselves in order to automate that end-to-end, whether it's a slice or single service. And that's where we start getting into sort of key documents like a WDM or WSON definition, using Yang as the modeling language, or maybe FlexiGrid for variable bit rates, or flexible lambda-based services. And then maybe also we need to offload path computation, so we'll need PSEP, path computation element protocol extensions, in order to sort of carry requirements and objective functions for computing path for fixed lambda or variable lambda services. Now, individually, these documents are rather important, but collectively, they're critical to actually automating network operation. Because once vendors actually follow the guidelines set out in the framework, the architecture, and then the how-to, we can start moving into device modeling. And we can ensure that we've got a generic messaging protocol that can then be used between multiple vendors to actually configure the devices themselves. Now, this will significantly reduce the time to deployment and the complexity of managing optical services, because we're moving away from proprietary management interfaces, command line interfaces, essentially sort of human intervention, to a programmable interface that's well-defined using a well-structured Yang model with all the available interface parameters over an automated interface. So what will this actually look like in the real world? Well, in the context of TeraFlow, we'll have our high-level interfaces, which could be BSS or third-party applications or end users, customers themselves. So there needs to be a northbound SDN-based transport interface. And there are a variety that we can use. You know, we've investigated and we're contributing and working with a few different northbound interfaces for sort of end-to-end service requests and network slice requests, both from the ONF and the IETF. So these effectively are Yang and UML models. There may also be some policy or intent that we want to also apply to any service request. You know, so what you want, not necessarily which technology layer to deploy it. We want to try to keep things as abstract as possible, the further up the hierarchy that you go. And then we've got the TeraFlow, the TFS, the TeraFlow SDN controller, which is now sort of managed within the ETSI consortium, that can be used as a piece of source code that you compile and then use based on some of these service interfaces that we're using for the northbound interface. They can essentially request connectivity through the TFS platform, the TeraFlow SDN controller. And Those interfaces are typically REST-based APIs. So one of the preferred mechanisms that we use is the RESTconf protocol. So already we're saying sort of service automation, not necessarily programmability at this stage, but as we drop down into the technology layer, the individual interfaces on the devices themselves, then we start to consider automation and network or device programmability. So we mentioned already the ACTN framework. So there will be components of ACTN in the SDN transport network controller, or if you're using the sort of TFS, the TeraFlow SDN controller, essentially it echoes some of the ACTN framework, and then you'll have several southbound interfaces to facilitate automation and network programmability. These might be ONF, depending, or TIP, the Telecom Infra Project interfaces, if you're using disaggregated ROADM or WDM or FlexiGrid technology, or you might be using IETF device models, and we mentioned WSON, so wavelength selective optical networking, or FlexiGrid. Those will be YANG-based models, and typically those are used on the more traditional network vendor equipment, but essentially they can be used over a generic messaging protocol such as NetConf. And those will then program the different sort of network layers. Maybe overlay will be a sort of packet overlay IP MPLS network, as well as the underlay. So it could be sort of fixed WSON technology or variable or FlexiGrid optical technology. And then maybe sort of some radio aspect as well, which could be sort of traditional devices, or it could be some disaggregated equipment. But by having this sort of top to bottom series of service, network, and device models over several well-defined generic messaging interfaces, it essentially facilitates network programmability. Now, it's not, of course, perfect. We wanted to talk about some of the risks. The risks here are really interoperability, making sure that vendors and third-party open source platforms have actually implemented the interfaces correctly, as well as the device, the network, and the service models, making sure that there's sufficient testing as well that's being conducted. And I suppose a weakness would be the time it takes in certain SDOs to actually develop this technology. It may be on the order of several months, or even as long as 1 to 2 years.
What are the requirements for SDN in the carrier networks? For mobile operators, the key requirements and expectations are reliability, scalability, and automation. Compared to the access networks that is facing a lot of challenges such as the high uncertainty, variety, and dynamicity, the transport network is relatively stable. Therefore, the challenge in scalability and automation could be addressed by using relatively simple mechanisms, such as the policy-based automation with semi-static configurations. However, nowadays, the transport network needs to be interconnected with and to support various types of network access networks, from indoor to outdoor radio access, from 3GPP to non-3GPP access network, or from private to public networks, not mentioning the addition of on-premise edge clouds. Due to the high complexity and demand for offering customized and differentiated connectivity services to the diverse access networks, the control and the management of transport networks are expected to be more scalable, intelligent, and efficient, which makes SDN a good and powerful candidate.
Hello everyone, my name is Carlos Natalino. I'm a researcher with the Chalmers Institute of Technology in Gothenburg, Sweden, and I'm happy to be part of this panel. So let me thank the organizers for the kind invitation. And here at Chalmers, we are part of the European TeraFlow project, and also the ETSI TeraFlow SDN open source group. So, given the title of this panel, that is Network Automation in Carrier Networks, Reality versus Myths, I made 5 slides that try to provoke and to bring up some discussion among a few things that still need progress. So I don't want to dismiss any technology or any progress that we have made over the past decades, but this is just again to spark some discussion. So let's get to that. Well, the first topic that I have here is SDN for carrier networks, requirements and use cases. And in this case, I would like to bring one attention to the myth that we may believe, that is that we can create a catalog of a few off-the-shelf services that will then be suitable for all our clients' needs. So for instance, we have this plot here, and this would be analogous of having a few points here that the clients would be able to pick. And of course, if you spread these options across all these different axes, then we would be able to compose a service. But what I believe that the clients need is a more flexible way to compose services. And this means that you need to have a more, let's say, soft range of values, of requirements that your clients or your users can then pick from specifically in each one of these different dimensions on a specific value that meets the requirements. So this means that at the end, you don't have off-the-shelf services, but rather your client will be able to compose its own service with all the flexibility of these different, let's say, dimensions that compose a service.
Deploying end-to-end services, what are the implications for network operators? For network and communication service providers, the end-to-end service deployment has at least 2 folds of implications. The first one is towards the customers, while the second one is towards the underlying network domains. To customers, we need to provide a self-service portal for them to order, create, and even manage the end-to-end services with an agreed SLA service level agreement. Then the ordered end-to-end service needs to be decomposed into network services provided by different and individual network domains, from access network to transport network and the core networks. The deployment process can be seen as an iterative process, as the end-to-end service SLA is translated into network domain service SLA, which could be further mapped to resource and infrastructure metrics that will guide the configurations of the physical devices, such as the switches, routers, firewalls, and even network interfaces. The deployment complexity will increase when the end-to-end service spans across multiple technology domains, administrative domains, or geographical areas, because it implies a high level of integration and interworking.
The second topic I would like to bring up is related to the deployment of end-to-end services. And one thing that I would like to point out is that our current tools, the algorithms that we use, and maybe also the data models that we use, are not yet good enough to understand how to take the best advantage of each technology when composing a service. So we still need to work on better models, better tools that would be able, for instance, bringing up this kind of infrastructure here, that would be able to take the best advantage of each segment of the network in order to compose the most efficient end-to-end service that still meets the requirements that we discussed in the previous slide. And what this means is that we need models that are very good at different network technologies. So we could have some optical fiber, some wireless technology, some millimeter wave. And we also need to have these models to deeply understand how the computational part behaves and works, such that we can ensure that whatever end-to-end requirements that we have are met regardless of the services.
Network disaggregation. When the end-to-end service spans across multiple technology domains, the end-to-end network is constructed in a disaggregated way by multiple vendors, which is beneficial actually for operators to avoid vendor lock-in. It also benefits us in terms of flexibility, because now we get to develop and invest in individual network domains or network components, depending on the available technology breakthrough. And we do not have to wait until all domains in the end-to-end context to be matured. As a result, it becomes more realistic to innovate and to support the new and specific service application or function requirements from customers. However, on the other hand, there is also a big challenge brought by network disaggregation. That is the integration complexity and the compatibility requirements between various components which are supplied by different vendors. This requires not only standardized APIs, but also close cooperation and coordination between vendors, which will eventually lead to a new ecosystem model.
The next topic I would like to bring up has to do with network disaggregation. And it's a myth that we currently believe that the monitoring and telemetry strategies we have today are intelligent enough. But the problem is that when we have, again, a network infrastructure that is so diverse and so dense, and then we disaggregate it, it means that we need deep monitoring of each and every device, each and every function. So this means that when we consolidate and we try to push all this monitoring data towards a database, be it a centralized database or a distributed database, it becomes very, very resource hungry. So what we need to do is that we need to develop here monitoring capabilities that can be more selective, and selective in several different dimensions, like in time, like in space, and like in feature, in the sense that which kind of information is being collected, is being processed, and is being stored. And just to add one more dimension here, we also need to have intelligent ways to do short, medium, and long-term storage of this monitoring data, because this monitoring data is also a great source of intelligence for our machine learning data-driven models. So we cannot simply drop them, delete them. So we need both more intelligent ways to collect this data and to select this data, but also how we can keep the knowledge in this data for the long-term operation of the network.
The exposure of a network capability actually is related to the end-to-end service deployment. Usually, the exposure of network capability is towards customers. In the transport network context, there are two types, or at least two types of customers that we refer to. The first one is for the enterprise or vertical customers who will order the connectivity services directly. And the second type of customer is peer network domains, such as access network or core networks. They need to interconnect through the transport network to create end-to-end services for their own customers. For the first type of enterprise customers, the exposure is usually customer-oriented and often more focused on the data exposure or some QoS-related capability exposure, because this will improve their customer and user experience. While for the second type of customers, that is the peer network domains, the expected capability exposure usually is more into the network or service management and operations, which is in practice a very delicate issue and needs to be designed and considered very, very carefully. Besides the API standardization, this exposure of network capability also requires proper definitions and classifications of what can be exposed, to which extent, and which entity the capability could be exposed, and at what level.
Moving on, the next topic is the exposure of network capability via standard APIs. And the point here is that although over the past few years or even a decade, we have made great progress with YAML, JSON, and its use across network, across the entire stack of the network, right? But the reality is that to move forward in a more efficient, sustainable, and dynamic manner, we need to adopt and to develop more efficient and more flexible data encoding schemes that will support the dynamicity and the efficiency that we want. And I put here as two examples, for instance, GraphQL and gRPC, that are examples that would be, let's say, closer to these more flexible, efficient data encoding algorithms. And I took the liberty of getting an example from this source just to exemplify to you what I mean by that. And basically this in the left hand side is an example of how JSON or YAML can be used in a REST API. And what we get here is that for each, when we send a request for an asset, for an object. And basically we get back always all the data related to that asset. On the other hand, in order to avoid wasting resources or even exposing sensitive data, what we have here in the right hand side is an example of the GraphQL protocol, where when we send the request, we already send what we want, but we also detail which fields we want from within that information. So this means that when we get the information back, we only get what we asked for. So we filter out anything that is not relevant and not useful, thus saving on the resource consumption and making the communication more flexible. So I believe that over the next years, we need to keep up with the discussions of how to improve and get always better and better APIs.
Automation. Automation is one of my favorite topics, actually. Automation and autonomy are the ultimate objective of network operations and service management. In 5G and the future 6G, automation is a must-have and a must-win battle for operators, while we are operating large-scale networks and offering differentiated services to diverse vertical customers concurrently with various access types. There could be actually many ways or enablers to realize automation. One of them is the software-defined technology. Nowadays, with SDN and NFV, virtualization and softwareization is indeed almost everywhere in the end-to-end network context. But we also have to be aware that software-defined technologies as an enabler indeed could enable automation, but with a certain cost, such as performance and the complexity. For example, in the cloud-native and the microservice-based environment, which we are deploying in our testbed, we always suffer from the incompatibility issue when one service, which could be an OpenShift or could be 5G as a core network functions. When one service is upgraded while the other services are not, then their interworking becomes an issue because of the incompatibility. So in the end, it becomes a big challenge for us to manage the version control in the large scale but disaggregated network if we want to softwareize everything. And this is, by the way, just the one single challenge. And there are many other challenges that we have to address while we softwareize everything in the future.
The final topic I would like to bring up in my presentation is about cloud-based network automation with software-defined everything. And one of the myths that I would like to bring up in this context is that we believe we have found the perfect balance between centralized and distributed decision. And the reality is that the optimality or the best place to distribute or to centralize the decision changes a lot. And this decision is very dynamic, so this needs to be reassessed every time there are meaningful changes in software and hardware. So for instance, if we look at this general TeraFlow architecture here, we have, for instance, a distributed attack detector that is used to detect attacks in layer 3, and this is placed in a distributed fashion because it does deep packet inspection. So it means that it does network packet processing. And if we were to centralize that functionality, we would have to spend and waste a lot of bandwidth in the network to transport all this data, and also it would be a quite resource-intensive functionality to do. So basically, this is where we can do some distributed processing and then centralize only the result of that processing to make a more efficient use of resources. But at the same time, we have also P4 that is able to place some intelligence in our networking elements, and this means that we need always to be assessing carefully which intelligence goes where. So basically, the reality is that we need to continuously assess this. And with this, I finish